Hi everyone, I'm Chen Beilu from Tsinghua University. Today I will introduce our work, Efficiency of Fairness, Carpooling Design for Online Ride-Hailing Platform. It's a joint work of Tsinghua University, the Chinese University of Hong Kong Shenzhen, and Didi Chuxing. Many people may have ever encountered a long waiting time during ride-hailing process. For example, we find that passengers always have to endure a long waiting time in transport hubs at midnight. The long waiting time comes from two periods. One is before passengers being picked up. We call it the queuing process. And another one is intra-station congestion after being picked up. We call it the congestion process. The long waiting time of passengers comes from short-term demand peak. And the demand peak phenomenon is very common. For the ride-hailing platform, it seeks to solve the problem by designing a good ride-hailing service. However, the queuing and congestion stages are with high randomness and complexity. The service design also couples in these two stages. Further, carpooling, or say ride sharing, is regarded as the most effective way to reduce users' waiting time and improve the ride-hailing experience. But when the platform needs to choose the optimal carpooling policy among several candidates, there is no valid metric on efficiency and fairness. So in this work, we seek to theoretically model and analyze the ride-hailing process, including queuing and congestion, and jointly design the optimal service rates. Then for the carpooling, we propose metrics on efficiency and fairness, and then show how to choose the best carpooling policy by the metrics. Now, we first analyze the queuing process. From the historical data in the right figure, we can find that the arrival process of passengers can be divided into two stages. The peak illustrated in the red bar and the off-peak illustrated in the green bar. We assume it is Poisson and steady. And we also assume that the arrival process of drivers is steady and can be decided by the platform. It means the service rate mu. Now, the queuing stage has been formulated into a two-stage queuing model. We can solve this model by queuing theory and busy period analysis. The upper bound and lower bounds of the waiting time can be derived as follows. In practice, the bounds are practically tight, so it can provide a very accurate estimation of the average waiting time. Further, we can find that the waiting time is nearly linear to 1 over mu. It means a larger service rate will reduce the average waiting time. For the congestion process, we follow classical congestion models and characterize it by differential equations as follows. By analyzing the differential equations, we can derive the following results. The first theorem indicates that the departure rate of passengers is limited, which means if too many drivers are dispatched, the station will be heavily congested. The second theorem indicates that the average waiting time is linear to 1 over 1 minus alpha mu, which means that the congestion time will increase while the service rate mu increases. So we know that the waiting times of the two stages change in different directions in mu, and we can choose an optimal service rate mu to balance the waiting time of the two stages, as well as to minimize overall waiting time. However, that's not enough. Carpooling, the ride sharing, is regarded as a powerful tool to further accelerate these two stages. Basically, there are three variants of carpooling service policies. They are the first come, first served policy, the carpooling first policy, and the average arrival first policy. These policies vary in different ways. How to choose the best policy under different circumstances is difficult. In order to solve this problem, we propose efficiency fairness metrics. Specifically, The efficiency metric is defined as passengers' average waiting time, and the fairness metric is defined as the mean absolute bias of the waiting time among different carpooling types. These values can be calculated by analyzing the carpooling process. We also propose the trade-off factor K. The platform can choose a favorable trade-off factor K and then select the policy which minimizes the weighted sum of those metrics. For example, for a two-passenger carpooling case, the analytical results can be derived as follows, where beta is the carpooling rate. We can find that the carpooling first policy is the most favorable policy when K is small. It means that carpooling first policy has a better performance in efficiency. And when K is larger, the average arrival first policy is more favorable. It means the average arrival first policy do better in fairness. Now we have already known how to decide the service rate and the carpooling policy. We combine them together and propose the integrated ride-hailing service design approach. First, the platform conducts the parametric estimation or the prediction. For example, it predicts the number of passengers who will come. Then it picks a favorable trade-off factor K and decides the optimal carpooling policy. After that, the platform can decide the optimal service rate. Finally, the platform can evaluate whether the expected average waiting time is acceptable or not. For our numerical studies, the data comes from Didi Chuxing platform. This figure shows the performance of different carpooling policies on efficiency and fairness in different demand cases. We can see that the ratio between efficiency and fairness is bounded for each policy. The blue bound line for carpooling first policy has a smaller gradient than that of green bound line of the first come first served policy. It means that the carpooling first policy generally has a higher efficiency, but more unfairness than that of the first come first served policy. And the average arrival first policy will produce no unfairness in our metric. Further, the dotted regression line is close to the real bound line, which means the regression is a good estimation of the bounds. This figure shows the relative performance of these three carpooling policies when carpooling rate increases. From figure A and B, we can find that the relative efficiency of the first come first served policy and the carpooling first policy first decrease and then increase. Their performance curves like a necklace. From figure B, we can find that the green points are accurately located on the line between blue and yellow points. It means the first come first served policy is a solution to reconcile the efficiency and fairness between carpooling first policy and average arrival first policy in a constant proportion. We conduct our service design on Beijing's real ride-hailing demand. We can observe that under the theoretically optimal service rate in figure B, most passengers only need to wait for less than 20 minutes during queuing and congestion stages. While with half and doubled service rate in figure A and figure C separately, the total waiting time will significantly increase, which is illustrated by the orange and the red pixels. This demonstrates the effectiveness of our service design. So our contributions can be summarized as follows. First, we theoretically analyze the service process, including queuing and congestion for service rate design. Next, we provide empirical metrics to evaluate the fairness and efficiency in the carpooling process. Then, we propose efficiency fairness trade-off analysis for carpooling service policy selection. Finally, we propose the data-driven integrated ride-hailing service design approach. And they are our references. And that's all. Thank you.